Welcome everyone to this conference presentation with the title of Uncharted Models for Dropout Prediction. It is a comparative study or benchmark in online learning presented by me, Houssam Bahi, and my supervisors, Dr. Karima Boussaha and the co-supervisor Professor Zakaria Laboudi of University Al-Bouaqi. Now to start with a small agenda, we will start by an introduction. After that we will dive into research questions and objectives, a small literature review to understand the past studies and the findings. After that we will dive into the heart of the paper, the methodology, and then we will conclude with the conclusion. There should be a part of questions and answers, yet if you are listening to this video there won't be, unfortunately. I apologize. So I thank you in advance, and we will finish by references. To start with, an introduction. To understand the problem in our community or in my field of research, it is about online teaching or online education. And one of the most important resources to democratize learning across online features is MOOCs or are MOOCs. What are MOOCs? MOOCs are massive open online courses. Small courses, duration about 6 weeks to a few months max. They use it on platforms such as Udemy and Coursera and so on. The platforms spend a lot of money, the teachers spend a lot of time creating them, so they are of great importance. And the goal of them is to democratize learning, provide quality learning for everyone across the globe, and to achieve the most or the harness the power of such courses. Now, what is the issue? The issue is the dropout in such courses. You find, for example, a high-level course provided by a great professor in MIT or Harvard and so on. They launch it for free. You find that students by thousands or hundreds of thousands, they sign up in advance, but you find just few hundreds that complete the course. So the high dropout rate, which sometimes exceeds 90%, is a huge problem for the educational data mining community. Now, coming to that, we need to find a way to get rid of this problem. The first step is the prediction, and after the prediction we can use like intervention or prevention strategies. So the first step is the prediction. Now, this is the topic of our paper here. The prediction in general, you find in plethora of research and papers done in this domain, but we notice few gaps. First, we have feature engineering. They have been used just like scratch the surface. They use just simple methods such as filters and statistical methods and so on. The same regarding machine learning, deep learning models. We have classical or traditional methods or models have been extensively used, yet complex architectures and some really promising models have not been used. The same for evaluation metrics. There have been a focus on some metrics that are not really suited for this problem. We'll talk more about it. And then there is a lack of focus. Very, very rare to talk about, or you find papers that discuss and do the optimization part. So as we said in the previous slide, the studies are suffering from such limitations and gaps. So in our paper we will try to do a comparative study in order to advance the field from the sides of feature engineering, the model selection and evaluation metrics, and the hyperparameters optimization and their complexity and the cost and so on, in order to advance the field. So like we said before, regarding the features, we have filters and statistical methods are widely used. Wrappers and embedding methods are rarely used. Models, traditional models and deep learning like simple architectures have been implemented. And we have evaluation metrics, a big focus on accuracy and precision, lack of use for metrics such as F2 score, and optimization that are rarely used. The key components, as you see in the right side of the slide, we said imbalanced focused. So as you can all see, there is not a balanced study or importance between models or data sets and so on. You find that in the majority of the studies they focus on 2 or 3 data sets and neglecting the rest, and the same for models, the same for feature engineering methods, the same for optimization. They only use, like, if they ever use it, they use simple ones like grid search, random search and so on. So there is an unbalanced focus. Secondly, we have the lack of confirmation of results. They don't check again the results of such models, and this can prove a problem later on if the results are not verified or stable. And thirdly, traditional methods are exhausted. We need to shift our focus on other type of models. And fourthly, the generalization issue, which is because most studies they use just one data set, 2 at the most, and they don't try or aim to provide a generalization or generalized solution. Coming to our methodology, this project or this study aims to push the boundaries of dropout prediction research by shifting away from single model benchmarking. So we will focus on a multi-data set exploration of feature engineering, the models, evaluation metrics, hyperparameter optimization. Starting with feature engineering, we will try to test and see the results and comparison between wrapper methods such as RFE and ensemble based feature selections, embedded approaches and so on. We'll try many combinations and we see the results, and all for the purpose or the goal of identify which feature engineering strategies generalize well across several datasets. We try to use at least 3, 4, 5 datasets at the least. Secondly, coming to the models, there are many promising models such as Learn++ NSO. It is really specialized for concept drift, which can be applied in our domain. We have the rare event logistic regression for imbalanced dropout data, perfectly aligned with our domain. We have the density or anomaly detection models, so we can treat like dropout or completers or some students that perform really complex pattern in learning. We treat them as anomaly and we can detect them in advance, the early detection of dropout. So we have really promising methods here. We have GNN to capture relationship students interaction using such as forums data and so on. There are really specialized data sets for that. We have also survival analysis to model dropout as a time to event process, because mostly we have features that are click stream data which provide like time to event data, and all for the purpose to not find like best model. There isn't such thing as best model, but to understand that it is recommended in such cases, or if the data set is like heavily time event featured, or I don't know, we can provide like a guide to which set of models or which family we can use best, and we get insights in general from them. Now coming to the evaluation metrics, we will try to focus more and explain why using F1 score and especially F2 score like primary metric for our evaluation of the dropout in all the field of data mining community. Also, we will talk about maybe other metrics such as MCC and balanced accuracy. And we will come to the hyperparameter optimization and fine-tuning. We will study and compare grid search, random forest, Bayesian, Optuna maybe, Zakaria, and many others. Or for the goal to, despite the no free lunch theorem, we can still get, like we said before, a practical guidance that will guide us through our research when there are like so much combinations to test, so we can reduce at least the number. We don't say provide the best combination in the model or the hyperparameter optimization, but at least we can reduce the number and close the gaps in this field so we advance. Coming to the dataset, why use several datasets? It is like an obvious questions. We need to find a generalized solution, so we need at least several datasets to confirm our results. Now, a conclusion. What are the key contributions of this study? First, a multi-dataset benchmarking framework that will improve generalizability and reduce dataset bias and close the gaps in the research in this field. Secondly, demonstrate that feature engineering has greater influence than models options or choice, and we will provide, hopefully, a critical insight for practitioners. Thirdly, reveals conditions where Uncharted models perform best, and then we will offer practical recommendation. And the same for hyperparameter optimization and tuning. And then finally, what is the most important aspect or the contribution of this paper is reframe dropout prediction research. And instead of asking which model is best or which configuration is best, we will advance to say which methodological strategy consistently improve prediction across diverse contexts. That's it. Thank you everyone for listening, and I will be open to any recommendation to enhance this study and to advance the field. Thank you all.